of x. I'm ignoring the normalization constants, okay? We don't need them right now. Our purpose is to concentrate on this. So here, this would be plus plus so what happens for the case of simple harmonic oscillator, one dimensional harmonic oscillator, I have only one set of A and A dagger, and there will be only one number operator, which is the product of A dagger and A. For the real scalar field theory, I would have only one wave equation, D'Alembert plus m square phi. This D'Alembert, if I can make space here, this d mu or d lambda, okay? So your mu takes on value 0, 1, 3. However, so this is called as this form of dynamics, or just writing instant form dynamics, and equal to plus minus and 2, 3. This is in light dynamics. So this is your progression, and now for the real scalar field theory, we have the Fourier decomposition or the Fock space decomposition for the field phi, which in terms of A and A dagger. So I have only one pair of annihilation and creation operators, and what it means, I have only one type of particles. Okay? In the theory, I have only one type of particles in the theory. However, if I have a complex scalar field theory, then I have two types of particles. So because my Lagrangian for 1/2 d mu phi minus 1/2 m square phi square, that is my real scalar field theory. However, for the complex scalar field theory, this would be d mu phi star or dagger as you like times d mu phi minus m square phi dagger phi. So I have two independent fields. Now phi and phi dagger are two independent fields, and therefore I need two independent sets of the annihilation and creation operators. So I introduce one A and one B dagger, and as you can see, if you take the dagger of this Hermitian conjugate of phi, this would be phi dagger, then I would have the Hermitian conjugate of B dagger would be B, e to the power ikx would be e to the minus ikx, Hermitian conjugate of A would be A dagger, and that of this would be e to the power ikx, right? So, in these two cases, and here you have, here in the first case, for the real scalar field theory, the wave equation or the field equation is your, for the complex scalar field theory, you have 2 plus m square phi equal to 0. Okay, one is the complex conjugate of the other, okay? One is the complex conjugate of the other. So phi star or phi dagger, as you like. Okay, so, but here, now let us look at, we keep these things in mind, and So for the oscillator in quantum mechanics, I have A dagger, and N. Okay. In real scalar field theory, I have A of K, A dagger of K, N of K, which is defined as A dagger of K, A of K. And for the complex scalar field theory, I have two sets. So, A of K, A dagger of K, N of K. This is and so now B of K, B dagger of K, and if you like, I could put a subscript here NA for the A, and I could put a subscript B here. So this is equal to so by putting the labels A and B, I can say that this set of three things, annihilation operator, creation operator, and the number operator for A type of particle. Okay, for example, N, B, B dagger, and NB are the annihilation, creation operators, and the number operators for the B type of particles. Okay, because you have two independent fields. Phi and phi dagger are two independent fields. In fact, in a short while, I will show you that I could, in principle, even break this up into two real scalar fields, phi 1 and phi 2, and I would have similar objects. I could describe this theory in terms of two real independent fields, phi 1 and phi 2, which are independent of each other. Okay? You see, if we are smart enough, we can see that this whole logic keeps working all the way to string theory and all the way to superstring theory. Now, here just to point out, without writing these any relations, you see, if now here everything would be bosonic, all right? All the field variables, all these operators, operators of course are at the quantum mechanical level, but even the variables, field variables at the classical level, they are also bosonic. And then I construct the Hamiltonian, and if I promote it to the quantum level, then this would be a Hamiltonian operator. Okay, so one could, in general, say that all the field variables, classical or quantum, they are bosonic. Okay, and so all the modes that in string theory usually one doesn't as a normal language, they simply keep calling them modes without saying annihilation, creation operators. Okay, but they are the Fourier modes. These are also Fourier modes, as you have seen, that you get them by the decomposition of phi. And phi do we call it the Fock space decomposition? There are two simple reasons. You can prove that n of k and n of k prime, you can prove this to be 0. The commutation relation of, so n of k commutes with n of k prime, or you can say that this is diagonal. Okay, I might for illustration purposes, I might even show you the explicit calculation for how to write down the matrix. Okay, in any of these theories. Okay, and this would continue to happen all the way to superstring theory. So, could I remove some of these things from here? Perhaps I could. So, let me remove everything. Okay. The only difference is when I talk about the Dirac-Spinner field, then you know Dirac-Spinner field is a describes Fermi particles, and therefore the at the classical level the field psi has to be a fermion. Okay, has to be a fermionic variable, and therefore if I would make the Fourier decomposition for this field psi, Dirac-Spinner field psi, then the corresponding annihilation and creation operators, they would be fermionic in nature. And we know that the fermionic variables, they anti-commute. So I might illustrate a little bit. And the equation of motion, of course, would no longer be the Klein-Gordon equation, but it would be the Dirac equation. Okay. So whenever I say wave equation, then we assume that it is always at the classical level. Okay. In classical physics, you have wave equations, but truly speaking, they are all field equations, and field equations can be quantum mechanical. If you promote your phi, psi, etc. to quantum mechanical